And hi, welcome to Lecture 8. So in this lecture, we're going to talk about exploratory factor analysis. So this will extend some of the things that we did in Lecture 7. So to begin, let's suppose that we are trying to measure statistics anxiety. And we have a scale that we're going to call it the PSYC-8. SAC meaning Statistics Anxiety Questionnaire, and the 8 refers to the fact that it is an 8-item questionnaire. Each of these 8 items is a Likert scaled item, so that means that people will rate them on a scale of 1 to 5, where 1 equals strongly disagree and 5 equals strongly agree. And here are the 8 items that people are asked to rate. Statistics makes me cry. My friends will think I'm stupid for not being able to use statistical software. Standard deviations excite me, etc., etc. So you have a copy of these notes. You can take a look at those items. So on Canvas in your course, there is a link near this lecture where you can download a file called psyc8.csv. So you'll need to go there and get that file if you want to play along with me on the lecture. Just download it somewhere on your computer. You may need to right-click on the link if your browser doesn't automatically download it. But nonetheless, save this somewhere where you can open it in JASP. And let's do that. And let's take a look at how the items correlate with each other. So I'm going to switch to JASP, and this is the data set that you should be able to open. This is the PSYC-8. Now you'll see that there are 8 variables corresponding to the 8 items, and there are a lot of rows. So this sample was on 2,571 people. Now, keep in mind, this is a simulated data set. These are not real data. I didn't just go ask 2,500 people, but this is kind of what it would look like if you were doing this for real. So the first step that we want to look at is see, do these items correlate with each other? Because what we're really trying to do here is see if this scale does measure this unified construct of statistics anxiety. If it does, each of the items should be related to each other in some way. So let's take a look at that. We'll go to regression and select correlation matrix, and then we'll just highlight each one of these items and drag them over into the variables box. Now I'm going to clean up this correlation matrix by unchecking the report significance check. I don't care if they're statistically significant. In fact, you'll notice that every one of them is statistically significant. That's simply because we have so many in the sample. This really isn't something that we care about right now. So if we uncheck that, that will clean up this correlation matrix. Now, in the last lecture, we had some sort of toy examples where you could go through and plot connections between the items if they were highly correlated. But if you were to do that in this matrix, you'll notice that none of the correlations are really much over 0.5. And most of them are in the 0.1 to 0.2, even less range. Some of them are 0.4. You know, how exactly do you make the connections here? What would the structure that this correlation matrix is hiding really look like? And the answer is it's hard to do that without some more sophisticated techniques. But that's exactly what exploratory factor analysis is designed to do. And that is the subject of this lecture. So what is exploratory factor analysis? Well, you might recall that the goal of factor analysis in general that we talked about in Lecture 7 was to uncover clusters of items that were related to each other in some way. What exploratory factor analysis does is it simply takes these clusters and it conceptualizes them as reflecting what are called latent constructs. These are sort of hidden underlying psychological constructs that are causing the variation in the items that you're seeing. We say that these measurements then vary along some number of dimensions or factors. We use those two words interchangeably. To give you an example of what we mean by this, consider, these are pretty popular if you've taken any psychology courses before. Sometimes people will refer to 2 dimensions of intelligence. You conceptualize intelligence as consisting of fluid intelligence and crystallized intelligence. Sometimes there are certain models of personality that posit that we have 5 dimensions of personality. You can remember them by the acronym OCEAN: openness, conscientiousness, etc. So that's what we mean by this. These are simply factors or latent constructs that contribute to this overall measure of either intelligence or personality, or in the example that we are dealing with today, the statistics anxiety construct. So let's go back to JASP and let's just do an exploratory factor analysis. It's really easy to do. We'll actually spend more of our time figuring out what it's saying. So this assumes, of course, you have a reasonably current version of JASP. This was I don't remember exactly when factor analysis was added, but you'll need to make sure that your version is as new as possible. So if you haven't updated JASP in a while, now might be a good time to do so. In this video, I'm using version 0.11.1, so keep that in mind. Now, to do the factor analysis, we go to the Factor button. And of the three options, we're going to choose Exploratory Factor Analysis. And this will open up a dialog box very similar to what you've seen with the correlation matrix. We're going to take each one of these variables, I'm going to highlight them all, and I'm going to move them or just simply drag them over into the variables box. And before I start paying attention to what pops out on the side here, and it usually is pretty fast, but I'm also recording a video at the same time, so it's a little slow on my computer. What I'm going to do are some very specific things. Now, JASP jumps to what it thinks you want to use, and by the end of this lecture, the output that you see will make complete sense. But for now, I want to use this as a teaching moment. I want to select some very specific things. So the first thing that I'm going to do is I'm going to change number of factors to manual, and I'm going to change the number to 2. Okay, and we'll talk about what that means in just a little bit. On rotation, I'm going to select orthogonal, none. All right, there's lots of options in here. I want it orthogonal, none. And then finally, I'm going to expand the output options, and I'm going to drag this little highlight slider down to 0. And that should do it. Now you should have an output that looks similar to this. So you may have been hoping that when you did the factor analysis in JASP that it spit out something like the little path diagrams that we did in the last lecture. It doesn't do that by default, but it says the same thing. Our job in this lecture is to figure out why it's saying that and how to see it. Okay, so let's go back to our lecture and then we'll refer to some of the things back and forth between the JASP menu and our lecture. So what exactly is it that we're seeing when we do this? Well, the main output is this so-called factor loading matrix. You may have seen that in JASP. That's this little table right here. We're going to talk about now what that means. So the idea behind the factor analysis, what factor analysis does as a model of the data, is it splits the total observed variance in the data into 2 components. Now, these 2 components come from aren't related to the 2 factors that I chose. Every factor analysis, regardless of the number of factors, does this. It splits the variance into common variance, which is the proportion of variance that is due to variation in the latent constructs, so the things that are underlying the measurements that we're seeing. And the other component is unique variance. So this is the proportion of variance that is unique to that particular item. Another way to say that is it's variance that's not due to the latent constructs. From a modeling perspective, this is variance that we are not capturing with the factor analysis model. Okay? So, common variance and unique variance. So, what are the factor loadings? Well, and again, what are the factor loadings? Let's see. They are these things right here. You'll notice that there's a table that contains the 8 items and then these 2 factors. We chose 2 factors here. And then a column for uniqueness. Okay, we'll talk about each one of these. What are these, though? These are the factor loadings. What they are, by definition, they are the correlations between each item and the given factor. Okay? So let's look at what that is. Pick question 1. This item 1, this was, I think this was statistics makes me cry. It is correlated with factor 1 at a correlation of 0.584, but it's negatively correlated with factor 2. Similarly, question 4 is positively correlated with factor 1, but negatively correlated with factor 2. So you can see each of these items has a different correlation with the two factors, the two latent constructs that are underneath this data. Now, these factor loadings are interesting because they themselves represent a decomposition of the variance. Let me show you what I mean by here. So if you were to take this correlation here, 0.584, and this correlation here, negative 0.305, and square them and add them together, you'll notice something. In fact, let me pull a calculator out. You might be able to see this in the video. I'm going to take 0.584 squared, and I'm going to add negative 0.305 squared. And let's see, I did something wrong here. Oh, it's because I didn't square the negative. Let me try that one more time. 0.584 squared plus negative 0.305 squared. Okay. Now, I don't know if you can see this on the camera or not, but I'll tell you that what I got was 0.434. That 0.434, you'll notice, is exactly the complement of 0.566. If as a percent, these two added together give me 43.4%, whereas this is 56.6%. Those add to 100%. Okay? That's no accident, because what these factor loadings are telling you is the common variance. If you square this one and square this one, so square the first correlation and the second correlation, and add them together, you get the common variance. And the common variance that for question 1 is 43.4%. That means that 56.6%, the remaining, is unique to this item. It's not captured by these two factors. Now, you can do that exercise with each one of these. But let's take a summary look at what all that is. Again, the sum of the squared loadings, that's what those correlations are called for an item, that's your common variance, and then 1 minus that common variance is the unique variance. So you could go to here, and for each item, you can tell me what the common variance is for that item, and also what the unique variance is for that item. Now, unique's not hard because it's just given to you in this uniqueness column. And of course, you can check that the sum of the squared correlations, these squared loadings, is exactly 1 minus this unique variance. So what the factor analysis model is doing now, just in summary, is it is splitting up the observed variation in each item into common variance accounted for by these factors, these latent constructs, and unique variance. Now the goal, of course, we'll get to this, but the goal is we want to capture as much variance as possible. So the higher this unique variance, I mean, look at item 2, it has a unique variance of 0.948. The higher that is, the worse the model fit, at least for that item. That might indicate that that item's not really a good item. We'll come to that in a little while. Whereas question 7, notice there's not much unique variance at all, which means most of the variation is captured with these two factors. Okay? So that's the factors. I mean, that's what JASP gives you, but it would be nice if we could actually see what these factors are. Now, you can't really do it directly in JASP, but if you were to plot the factor loadings on 2 dimensions, so like an X and a Y axis, then you could actually see something. That's what I'm going to do in the lecture notes now. So here's what we're going to do. To see the factors, we're going to plot the loadings for each item on factor 1 on the X-axis, and the loadings for each item on factor 2 on the Y-axis. So for example, item 1 was 0.5 something, and then negative, let's see what it was, negative 0.305. So on a plot, that would go out to here on the X-axis and down here on the Y-axis. So you can see item 1 shows up here. Item 2 would show up here, item 3 would show up here, etc. So each of these 8 items now occupies a position in this factor space, in these 2 dimensions that the factor analysis model has done. And so this is the clustering. You can kind of see that these items are clustered together, these are clustered together, and these are clustered together. Moreover, you can see that these items here kind of, so if you look at these 6 items, 1, 4, 5, 8, 2, and 3, they sort of vary along this dimension. You can see where my mouse is going, whereas 6 and 7 vary along this dimension. So maybe if we were able to sort of rotate our heads a little bit, let me show you what I mean by this. If we could rotate the axis to these red axes, this might actually be a slightly better way to look at the pattern that we're seeing in the data. And you can do that in JASP. It's called an axis rotation, or a rotated factor model. We get it by going to rotation, orthogonal, which means that the axes are 90 degrees, but we're going to choose varimax. Okay? And when we do that, you'll notice that the factor loadings change. Now the uniqueness, so the amount of common and unique variance doesn't change, but the factor loadings change. If we were to go back and plot these factor loadings again for each item, here's what it would look like. You'll notice now that this is just the same patterns, the same items are clustered together, but instead of being kicked over to the side like they were in the previous, they're now sort of brought in line with, I know you can't see what I'm pointing at here, but they're brought in line with these red axes. It's like I've just taken the space and rotated it by approximately 40 degrees. And so that's exactly what you see. This is what we mean by a rotation of factors. Essentially, the variance decomposition, the model remains the same. The only improvement by the rotation is in the interpretability of the factors. If we're trying to figure out what these factors mean, it's really much easier to do when we see it in this rotated space. So now we're actually ready to get something out of this factor analysis. So let's take a look first. Notice we have two dimensions, one going this way and one horizontally, one going vertically. You'll notice that the horizontal variance is everything except items 6 and 7. 6 and 7, they kind of occupy their own direction, right? Why might that be? Well, let's go back and look at the items. What is different about items 6 and 7? Well, 6 and 7, you'll notice, are all about computers. They don't say anything about statistics themselves. Everything else mentions the word, at least the word or a concept with math or statistics. 6 and 7 are different. We're seeing now that they're different. When you look at this factor analysis, when you look at this picture, you are seeing that 6 and 7 are on a different factor. They're loading heavily on a different factor than these are. So perhaps items 6 and 7 reflect something different than statistics anxiety. Maybe they represent something about computers. As a test developer, this is now a first very important step in my scale development. I'm now looking at items 6 and 7 and think, well, do I really need those in this SAC 8 questionnaire? Are they really capturing statistics anxiety? Okay. So let's now think about our role as a scale developer, right? Let's go back to JASP. Our goal is to see that the scale measures what we think it does. JASP will help us see that a little bit better with a cool little option. Now, you'll remember at the very beginning of the factor analysis, I said, take that little highlight slider and scroll it down to 0. Well, let's now go back to the default. Let's go in JASP and let's choose highlight equals 0.4 and see what happens. So down here under output options, let's move this up to about 0.4. Okay? And you'll notice something magical happens in the factor analysis output. The factor loadings disappear. What it's actually doing is simply hiding all loadings that are less than this threshold. It's hiding those that are less than 0.4. Essentially, what you're wanting to see as a scale developer is which items load heavily onto which factors. So if we hide all of the, quote, low loadings or small loadings, that can help us see this. And what you can see is something, you can see actually a lot of things. First of all, you can see that item 2 doesn't load heavily onto either factor. That's not surprising considering that almost 95% of the variation in question 2 is due to that question itself. It's not due to variation in the common factors. So it could be that item 2 is just not capturing anything related to statistics anxiety. That makes item 2 a not very valid indicator related to statistics anxiety. As we can see here, questions 6 and 7, as we already saw in our plot, they load pretty heavily onto factor 2. So maybe factor 2 is that factor related to computer anxiety or something like that. And then the rest of the items, 1, 3, 4, 5, and 8, they load pretty heavily onto factor 1. You'll notice that question 3, it has a negative loading. Why might that be? Well, again, if you go back and look at the original items, item 3 is actually worded oppositely from the rest of the items. So the rest of the items, the higher you would rate, the more statistically anxious you would be, right? But item 3, if you're statistically anxious, you're going to be pretty low on the excitement that standard deviations give you. So we're seeing that, again, in the factor analysis with this negative loading. So that's really pretty cool, right? This is sort of by default what JASP will give you. It will give you this sort of structure that you can then begin to see in your factor analysis. So let's go back and just kind of catch up with where we are, and then we'll finish up with 1 or 2 extra things. So in terms of scale development, these are the outcomes that we just saw. We saw, again, to recap, item 2 doesn't load heavily onto either factor. Items 1, 4, 5, and 8, they load onto factor 1, which we might call statistics anxiety. Again, we're making that up, right? We think, due to the face validity of these items, that those items are related to statistics anxiety. Items 6 and 7, again, they appear to load onto something completely different, another factor which we might call computer self-concept. And then item 3, it loads onto factor 1, but it's negatively. That's because it's a negatively worded item. There's nothing wrong with that. It's just that you're seeing that in the factor analysis. So we're actually accidentally getting exactly what we want in exploratory factor analysis. We are achieving something called simple structure. By the way, sorry for the typo there. What is simple structure? Well, it's a goal, right? It's something that we would like to have when we're developing a scale. Here's exactly what it means. Simple structure is what you get when each item loads highly onto one factor only. So you pick any item in JASP right now, and you'll notice that it loads onto one factor only. It doesn't load highly onto 2 factors. And that's important because you want each item to reflect one and only one construct. Also, each factor has a high loading for only some of the items. What that then means is that you are capturing multiple dimensions among your items. I will mention that sometimes this may require something a little more advanced. This may require something called an oblique rotation. What that means, and I'll show you exactly what that means in a second, is it allows for your factors to not be independent. It allows for your factors to correlate some. Let me show you geometrically what that means. Notice that when we had this original factor structure, it might actually even be better to let those axes not be orthogonal, to cross at a non-90 degree angle. In fact, if we make this angle, I worked it out earlier, if we make this angle, I don't have my notes here, I think this angle is something like maybe 42 degrees. I think that's right. But anyway, it doesn't matter. The whole point is if we were to put our red factor dimensions in this direction, you'll notice that we get a lot closer to where the items are living than if we do like this, right? The items are not very close to the axes. So let's just see what we can do there. If we were to do this, this is what's called an oblique rotation. You can actually do this in JASP. Let me show you how to do that. Instead of orthogonal, we choose oblique. We'll use Promax. There's many methods here, but Promax is the default. And it will update all of these factor loadings. Again, it does not change the variance that's accounted for by the model, but it does update the factor loadings. If we were to plot these factor loadings onto a 2x2 grid, just like before, here's what we would get. You'll notice now that we have exactly the same patterns. We have 6 and 7 being off in their other dimension, but again, they're now closer to the axes that reflect the underlying dimensions that these items are varying on. So again, oblique rotation just simply improves the interpretability, and its main goal is sometimes you'll have to use it to achieve that simple structure that we were talking about. Now, I mentioned that this lets the factors correlate. You can see this here. If you were to go into JASP and check factor correlations, so let me show you where that is real quick, right down here. you'll see then that it'll give you the correlation between factor 1 and factor 2 of 0.748, so that's pretty highly correlated. If we did the orthogonal rotation, you'll notice that correlation will decrease. It goes down to 0.144. Again, the idea of orthogonal is you want the dimensions to be independent from each other, or oblique rotations let them correlate some. So again, the whole point of the rotation is not to improve the fit. The fit is the same. The fit you get from this uniqueness and the common variance. The point is interpretability. Okay, the last thing that we want to talk about in this lecture with factor analysis. We've talked about how to do the factor analysis, how to interpret it. The goal is to achieve simple structure, and sometimes you'll have to do oblique rotations for that. The last thing is to answer the question of how many factors should I choose? Okay, so how do we do this? At the beginning of the lecture, I told you let's choose 2 factors, but that was just me telling you that. In general, how should you do this? Well, I'll just say there are a lot of rules of thumb out there. You Google factor analysis, you're going to get a lot of different ways to do this. I'm a modeler. I prefer using something called model fit to inform the number of factors that we use. To illustrate this, let me walk you through the following. First of all, what is factor analysis as a model? Well, remember, we talked about this. Factor analysis simplifies the data structure by grouping your items into a smaller number of factors. As such, the recovered structure, the approximate structure that you would get from this model, is only approximate. To illustrate that, let's walk through how you would recover the correlation between 2 items from the factor loadings. So let's assume that you have orthogonal factors. So it is a fact from the factor analysis model that you can get the correlation between items I and j, and we'll do an example in a second, but you can get the correlation between any 2 items by taking the loading of the first item on factor 1 times the loading of the second item on factor 1, and then adding that same product for factor 2. So the loading of the first item on factor 2 times the loading of the first item on factor 2. So to illustrate that, let's go back to JASP and let's estimate the correlation between items 1 and 3. So I'm going to do it in JASP, but I've got it summarized down here. So for items 1 and 3, let me uncover all of these loadings again and go back to my orthogonal rotation. All right, and let me go back to the original, which was no rotation. There we go. All right, so I want the loading of the first item on factor 1, so that's 0.584, times the loading of the third item on factor 1. So that's negative 0.555. So I'm going to multiply 0.584 and negative 0.555. And then I'm going to add to that what I get by taking the same items but on factor 2. So I'll take negative 0.305 for item 1 and 0.104 for factor 2. So I'm going to take 0.584 times negative 0.555 and then add negative 0.305 times 0.104. And that's what I've got here. And if I do that, I get a correlation of negative 0.355. Well, how did we do? Well, the actual correlation, as you'll be able to see in JASP, was negative 0.337. That's different, but that's not surprising because the factor analysis model is an approximation of the data structure. So there's a little bit of error. The question is, how much is acceptable? A lot of different indices for this, but what I like to use here is what's called the RMSEA, the root mean squared error of approximation. The reason I like this is because this is the same kind of error that you've always computed. It's the deviation from the mean, you square them, and then you add them up and take the average. The root mean squared, and then take the square root. So it's the root mean squared error of approximation. As a benchmark, Brown and Kudik in '93 recommend that anytime you have this root mean squared error less than 0.08, you've got an acceptable fit. So let's go back to JASP and show you how to do that. So down here in the output options, let's take a look at this. If we look at additional fit indices, you'll get a table, here it is, that has lots of indices, but one that it has in particular is RMSEA. Now you'll notice for this 2-factor model, the RMSEA is 0.075. Does it change if I do a rotation? Well, let's do that. You'll notice the loadings change, but none of the model fit indices change. What if I do an oblique rotation? Again, the factor loadings change, but none of the fit indices change. This is not surprising because remember, as we've said, the factor analysis takes the variation and splits it into unique variance and common variance. Those don't change. The only purpose of rotation is to help with interpretability. So really the only thing that's going to change how the model fits is the number of factors that you choose. So I could go up to 3 factors, but let's start with simple. Maybe all of these items are reflective of one construct, one dimension, one factor. Let's do that. Let's change the number of factors to 1. And I'll press tab there. I get 1 factor. You'll notice now the RMSEA is 0.102. So this is higher than that threshold of 0.08. So we would call a 1-factor model not a good fit. Not surprising because we've already seen that items 6 and 7 don't seem to really map on to this factor of statistics anxiety. So we go up to 2 factors and press tab. We get our original fit. We get the 0.075. So we'll say this is acceptable. You can, of course, improve the fit by adding factors. If you go up to 3, you're going to get your root mean squared down to 0.02. Go up to 4 factors, it's going to go down even farther. This is almost by definition. In fact, it's below the threshold. It's not absolutely 0, but it's below the threshold of 3 decimal places. But when you do this, you lose parsimony, right? The whole goal of model fitting is to make it as simple as possible, but still reflect as much as possible. So a 4-factor model, that's not simple at all. I think the best balance of model fit and parsimony is the 2-factor model. This gets you right down here to a root mean squared below 0.08. It gets you onto 2 factors that are easy to interpret. As we saw before, we can interpret these factors as, let's see this, we can interpret these factors as, it's kind of balking on me, as some items reflecting statistics anxiety and a couple of items that are reflecting something about computers. So that's exploratory factor analysis. The exploratory part is exactly what we just did, finding that optimal balance between the number of factors and model fit. And that is one of the fun things about computational psychological science, is fitting things while making them as simple as possible to explain. So for this example, we've got a nice 2-factor scale. As scale developers, we might say, hey, this scale represents 2 factors. Or we might say, hey, let's remove items 2, 6, and 7 because they don't add anything to this. And then we've got a nice 5-item questionnaire. So the sky's the limit here, and this is sort of the art of scale development. So that's all for now. That's a bit about factor analysis. If you have any questions, let me know. Other than that, that's all, and we'll see you next time.